let's talk about the distribution of a random variable. For now, we'll assume that our random variables can only take on a finite number of possible values. This piece of notation here has a very specific meaning. This is the probability that random variable capital X is equal to the value lowercase x. And this is why we stressed before that it's important to remember that capital letters denote the names of random variables. For example, here, this is the probability that the random variable capital X takes on the value or is equal to the value 20. And so little x will represent the specific values that the random variable can take on. The distribution of a random variable describes how the total probability of 1, or 100%, is split across all of the possible values that our random variable can take on. One of the properties of a distribution is that each of the probabilities must be between 0 and 1, so they can't be negative. And the sum of all of the probabilities of the values that a random variable can take on must be exactly equal to 1. So if we sum over all possible values x of our random variable, the sum of those probabilities must equal 1. Here we have an example of the distribution of a random variable, and we call this specific notation a distribution table. Now, and we'll switch to the iPad really quick here. In a distribution table, over here on the left, we have all of the values that the random variable takes on, and in this case, x takes on the values 3, 4, 6, and 8. On the right, we have the probabilities of our random variable x taking on these specific values. And so given the distribution table, we can compute a bunch of related probabilities. So for example, the probability that random variable x is equal to the value 4, we can read this directly from the table as being 0.2. The probability that random variable x is less than 6, well, we can look at the table and think to ourselves, when is x less than 6? In our case, that happens when x is equal to 3, or when x is equal to 4. And so here, this will be the probability that x is equal to 3 plus the probability x is equal to 4, because this is an OR, which gives us 0.1 plus 0.2, which is 0.3. Another calculation we could do based off of this distribution table is finding the probability that x is less than or equal to 6. And well, this happens when x is equal to 3, or when x is equal to 4, or when x is equal to 6, right? And then since it's less than or equal to, we include the x equals 6 case. And so now this will be 0.1 plus 0.2 plus 0.4, which is 0.7. As a last example, the probability that x is equal to 7 from this table is 0, because all of the probability is split up amongst the values 3, 4, 6, and 8. You can see that 0.1 plus 0.2 plus 0.4 plus 0.3 add up to 1. So the probability that x is equal to 7 is 0. The random variable we just looked at only takes on 4 possible values, 3, 4, 6, and 8. And so we can visualize its distribution using this lollipop plot or stem plot that you see here on the left. But it's useful to think of our distribution as being binned, and this helps us think of probabilities in terms of areas. So for example, we could think of having integer bins. So for example, here would be the bin for 1, here would be the bin for 2, this is the bin for 3, this is the bin for 4, this is the bin for 6, this is the bin for 8, so on and so forth. And the reason this is helpful is because the probability that x is between 3 and 4 inclusive is just the area of these two bars. And so you can see the width of this is 1 and the height is 0.1. So the area of this is 0.1. The area of this one is 0.2. So we add these two areas, we get 0.3. And so now, since this is a discrete distribution, we could just look at the heights. But we will quickly want to look at random variables that are continuous or have an infinite number of possible values. And in such cases, we can't just look at the height to compute a probability. We instead need to look at areas. So the top two distributions here are of a continuous random variable. And you can see here we have the bars for x is equal to 7, x is equal to 8, and x is equal to 9 shaded. And so the area of this red region is equal to the probability that x is between 7 and 9 inclusive. These bottom two distributions are of a continuous random variable, and it seems like on the x-axis, this shaded region starts around 6.8, I want to say, and ends around 9.5. And so the area of this red region is equal to the probability that this random variable x is between 6.8 and 9.5. So it's useful to think of probabilities in terms of areas, regardless of the distribution type. Speaking of the types of distributions, we like to think of probability distributions as belonging to one of two categories. The first category is discrete. And so we say a distribution is discrete if the set of possible values it can take on is either finite, so some finite set like 3, 4, 6, and 8 that we just looked at, or countably infinite. Now, if you've never heard this term, countably infinite, do not worry. Another way of thinking about this is a random variable is discrete if the values that it takes on are separated by some fixed amount. So for example, we could have some random variable that could take on the value 1 or 2 or 3 or 4 or 5 or so on and so forth. Even though there are technically an infinite number of possible values it could take on, we say that this is discrete because the values that it could take on are separated by some fixed amount. The other main category of probability distribution is a continuous distribution. And so here, the set of possible values that x can take on is neither finite nor countably infinite. And so here, typically, x can be any real number in some interval. So it could either be, any real number period or any real number, between two bounds. So for example, it could be any real number between 0 and 1. And in this class, we will mostly focus on discrete distributions, but you should know that continuous distributions exist because they will reappear. We'll wrap up by looking at some of the more famous discrete and continuous probability distributions. The most common discrete distributions are the Bernoulli and binomial distributions. I won't talk too much about those right now because the next entire video is dedicated to them. One thing to note, though, is that these variables in brackets are called parameters. The parameters of a distribution are the constants associated with it, and the parameters describe the values that the distribution take on and what the shape of it looks like. And we will see how these parameters p and n and p describe Bernoulli and binomial distributions in the next video. Another common discrete distribution is the one that's uniform on a finite set. A common example of this is a single roll of a standard die. Right? The roll of a die is distributed uniformly on the set 1, 2, 3, 4, 5, and 6. There are 6 possible outcomes, and each of those outcomes occurs with probability 1 over 6, because the size of the set is 6. Two of the more common continuous distributions are, again, the uniform distribution, but instead of being uniform on a finite set, it's uniform on some specified interval on the number line. So for example, the one that's uniform on the unit interval takes on any real number in the range 0 to 1. And of course, our old friend, the normal or Gaussian distribution that has two parameters, mu, which is its mean, and sigma squared, which is its variance. And we won't talk too much about the normal distribution in today's lecture, but as I mentioned earlier, it will reappear later on in the semester.